Nano world is very interesting from a scientific point of view. Nanotechnology, which is based on nanoscience, is directly related to future industries and business, particularly in the biomedical and environmental fields. Therefore, it is extremely important for youngsters to understand the nano world and apply nanoscience and technology to the development of future devices and machines, which should lead to some industrial revolution. So I'm going to give a special web lecture on nanotechnology. Okay. Good morning.
Good morning.
Have you ever heard about nano? Yes or no?
Professor Toru, could you explain about that?
Okay. Have you got any idea about these molecules?
Yes.
So this molecule is composed of 60 carbon atoms. What is it called?
Fluorine.
Oh, you're clever. Yes, C60, fluorine, and buckyball. What about this? This is composed of 70 carbon atoms. Okay? This is also fluorine, one type of fluorine. Okay, rugby ball. So everything has changed after this discovery of fluorine. Okay? So as I said, I'm going to show you the nano world. This is the outline of my today's talk. I show you nano world and nanomaterials. I briefly introduce nanorobotics, and I tried to apply those nanorobots to biomedical studies. Okay. What's nano? Nano is a prefix. Okay. Do you know milli? What does that mean? What does that mean?
10 raised to minus 3.
Okay, 10 to the minus third or 3.
Yes.
Doesn't matter. Anyway, you know millimeters, milligrams, milliseconds, milliliters. What's MP? Okay, so micro, what's micro? 10 to the minus 6th. And nano is 10 to the minus 9th. Okay. Pico, femto. What's 10 to the minus 18th? What is it called? Atto. Yeah, good. Yeah, so I want to change my center's name from the Bio-Nano Research Center to Bio-Atto Center. Okay. So all the materials are composed of molecules. Molecules are composed of atoms. Atoms are composed of nuclei and electrons, right? In our macroscopic world, we live in continuum media. That means solid and fluid. Fluid means liquid, gas, and plasma. All right, the typical size of an atom is 0.1 nanometers. And the time scale is completely different, of the order of femtoseconds, okay, very quick. But in our world, we are composed of so many molecules. The time and length scales are completely different. You can explain the molecular structures and dynamics by quantum mechanics. So you have to study quantum mechanics. In the macroscopic world, you need thermodynamics. We use the temperature and pressure, okay? But what we are sensing is ridiculous. We can't detect the molecular motions, okay? What we are sensing is some statistical information of those molecular dynamics. That's why you need to study statistical mechanics. But we really don't know what's going on in the nano world. That's why I started studying nanotechnology and science. Let me focus on the scales. So the Earth is huge, okay? But you like football? Yes. The World Cup? Yes. No? Okay. The diameter is about 22 centimeters. Your favorite fees, lice, okay, so millimeters. Okay, human hair. Sorry, that's mustache. And, so the size varies. So you're young, much younger than I am. So my hair is much thinner. Okay, you're lucky. See? Okay. So red blood cells, several microns. And the size of viruses varies from 5 up to 300 nanometers. So you can't stop the invasion. Be careful, right? And a helical diameter of a DNA is approximately 2 nanometers, right? Do you know this? This is a single wall carbon nanotubes. The internal diameter is approximately 1 nanometer, all right? Very tiny. And as you know, the diameter of C60 is 0.7 nanometers, okay? So, as I said, what's going on at the nanoscales? The deviation and fluctuation become significant. So because the number of molecules is much smaller than in the macroscopic world. In our world, so the number of molecules is huge. So the standard deviation can be ignored, okay? And then molecular diffusion time is very short. That's why we are producing nano microchips for the detection of diseases. The detection time should be very short, okay? And classical fluid mechanics doesn't work. Similarity doesn't apply. So you need new mechanics, right? So I hope you really find, new mechanics. And surface effect becomes significant. So in a sense, all the phenomena are determined by the surface reaction or surface interactions, okay? The quantum effect appears. I really like quantum effect. It's fascinating. This is an electron, negatively charged. There's an anode. So electron is attracted by anode. But because of this barrier, it can't go through, right? That's normal. But under some electric conditions, it can go through the barrier. You know that? This is one of the typical quantum effects. It's called tunneling, electronic tunneling. We also applied a vertical magnetic field, okay? Then, under some magnetic conditions, electron can go through the barrier without breaking the barrier, okay? That's amazing, fascinating. Let me focus on nanomaterials. This is the pressure temperature phase diagram of carbon dioxide. Along this curve, you can clearly see the liquid and gas, and there's an interface, okay? But this curve terminates at the critical point. At the critical point, fluid is not transparent anymore. Fascinating, so amazing. And beyond the critical point, which is called supercritical fluid, it's transparent again, but there's no interface. It's commonly used in chemical industries. By the way, my name is Toru. You know, that means transparent. Okay. Anyway, I really like the critical point because it's not transparent. What's going on there? At the critical point, large molecular clusters are formed. Even if you change the scales, you see huge molecular clusters are formed, and percolation transition occurs. The molecular structure becomes fractals. These are typical second-order phase transition features. Fascinating. Wilson won the Nobel Prize for the analysis of the critical point in 1982. Amazing. So my idea was to irradiate photons. Photons definitely hit the molecules. If I irradiate ultraviolet photons, UV photons, I thought electrons may be excited, okay? So we did an experiment. By the way, the critical temperature, generally speaking, is very low. In the case of carbon dioxide, it's only 31 degrees Celsius at room temperature. And as I said, we irradiated UV photons into carbon dioxide under critical conditions. Then what happened? We got carbon particles. So I was really excited, happy, because carbon dioxide was dissociated into carbon and oxygen at room temperature. I thought, it's amazing. So perfect spheres are synthesized. And then I mixed foreign molecules, such as metallocene, with carbon dioxide. Then we did the same experiment. We've got magnetic nanoparticles covered with graphitic layers. So metallic nanoparticles are usually cytotoxic. But thanks to the graphitic layers, and they are biocompatible, and they are magnetic. Okay? And if you change the pressure slightly, you get the non-spherical particles. This is also fascinating. You see, these are very useful for the detection of a very low number or low concentration of biomolecules and bioimaging. Okay? Fibers are composed of C60, easy. Simply, you just place C60 in CO2 under critical conditions. Then we got fireworks. Okay? They are also composed of C60. See, this is very important for me. As I said, the surface area becomes huge on nanoscales. Then if you use C70, amazing. We get the micro tubes. I don't know why they're produced. Don't ask me. So you should know better. Then, briefly, I show you our nanorobotics. So we applied a rotational magnetic field to manipulate our magnetic particles. These are top views of magnetic nanoparticles. By changing the direction of rotational magnetic field, you can change their motion, okay? But they haven't got a name. Have you got any idea about their name? No? Let me know later. Okay. This is carbon nanotube. In fact, iron is encapsulated. So we've got the magnetic carbon nanotubes. And we also attached the fluorescent molecules, okay? So you can visualize those, so the movement of carbon nanotube, right? So easy. Then we applied those nanorobots to biomedical studies. But the problem was that the nanomaterials are basically hydrophobic, as you know. So we can't use them to biomedical studies. So we modified the surface of those nanoparticles with biomolecules, okay? So that they became hydrophilic, okay? And then we immobilized enzymes on the surface of our magnetic particles, and we rotated. Then the activity was increased. The activity became the maximum at a frequency of 5 Hertz. Okay? You can encourage the activities easily. And you can attach your magnetic particles utilizing antigen-antibody reactions. Okay? This could be your cancer cells. Then, as I show you, the fireworks, we modified the surface with the antibody molecules and captured successfully our target molecules or particles. Okay? Now, magnetic carbon nanotubes can be attached to the surface of your target cells. So you can move the carbon nanotube to give stress to kill the cancer cells. If you also apply high-frequency AC magnetic field, it can be heated up. Okay? The temperature increased, and then you can kill your cancer cells, okay? It's called hyperthermia. Nanomaterials are very interesting. The color can be changed by changing the size, right? So this could be very good for your nano fashion and nano cosmetic. That would be a future industry. Interesting. Those cancer cells were visualized using our nanomaterials successfully. So for the future, nanoscience means physics, chemistry, and biology are united at the nanoscales. So no distinction. So don't worry about that. So what is your background?
I'm from biology.
Okay.
Chemistry.
Physics.
Oh, good. But forget your original study. So all are united. Okay, that's fascinating. Then what can our nanorobots do? Okay, as I said, nanoimaging of your target molecules and cells, nanotreatment of your target cells. You can give stress, or you can heat it up by applying high-frequency AC magnetic field, and you can deliver drugs to your target cells. That's our future aim. Actually, that's what we are doing now. So I hope you join our activities, okay? Yeah. So let me finish with a nice quote made by great scientists. The future is uncertain, but this uncertainty is at the very heart of human creativity. Ilya Prigogine, do you know Ilya Prigogine? He won the Nobel Prize for Chemistry in 1977. Okay, really, so I know you are worried about your future, but don't worry. It directly leads to your creativity, okay? Imagination is more important than knowledge. Knowledge is limited. Imagination encircles the world, see? Albert Einstein. So knowledge is up to date, see? This was impossible. People couldn't imagine this before 1985. Now, everybody knows this, okay? So knowledge is knowledge, but you have to think. Finally, anyone who has never made a mistake has never tried anything new, okay? So that's true. So don't worry about your mistake. Your mistakes may lead to your new discovery, okay? So welcome to the Nano World. Please join our world. Let me finish this special web lecture. Thank you very much. Thank you.